Limits from tables and graphs. Here we're going to explore this concept of a limit. If we look at the function f of x as x squared minus 25 over x plus 5, we find that x equals -5 makes the function undefined. And in fact, you may recall when we studied rational functions that the fact that the numerator and denominator share the common factor of x plus 5 means there's a whole. At x equals -5. So we're going to explore what's happening to y as x gets closer and closer to -5 on the left as well as the right. So created a table of values, and -5 is not in the domain, it makes the function undefined. And I picked values slightly smaller than -5 and slightly larger than -5 to see what's happening to y as we get closer and closer to -5 for x. And I see as x gets closer to -5, the y values get closer to -10. We say that as x approaches -5, f of x approaches -10. And we can express this sentence in a mathematical notation called limit notation. We use an arrow for the word approaches. So suppose that f is a function defined on some open interval containing the number a. The function f may or may not be defined at a, and the limit notation, as you see displayed, is read, the limit of f of x as x approaches a equals the number L. This means that as x gets closer to a but remains unequal to a, the corresponding values of f of x get closer to L. So let's practice using a table to evaluate the limit. So we're going to look at the limit as x approaches 0 of x squared minus 9x over x. So we pick values close to 0 on the left and on the right. And we're going to plug those values into the original function to see what we get for y values. So I've given you suggestions in the table. We're going to start with x is -1/10. So we want to plug -1/10. So again, you're just plugging it in to the original function. And I get -9.1 approximately. When I plug in -0.01, I get -9.01. And when I plug in -1/1000th, I get -9.001. At 0, it's undefined. And then we're plugging values in on the right side. So when I plug in 0.001, I get -8.999. 1/100th, I get -8.99. And positive 1/10th, I get -8.9. So it appears that as x gets closer to 0 on both sides, that y is getting closer and closer to -9. So we would say the limit as x approaches 0 of x squared minus 9x over x is equal to -9. We can also find a limit by using a graph. So if we have the graphical representation of the function, we can explore what's happening to y as x approaches the given value. So number 2, you're given a graph, and we're going to use that graph to find the indicated limit and function value. So there's two parts to this. We're going to find the limit as x approaches 1 of f of x. So what we're doing is we're looking at the graph on both sides of 1. So if we follow the graph as x approaches 1 on the left, and then on the right, we're seeing if y is approaching a particular value, and it is, it's approaching 3. So remember that the limit is just asking what the function is getting close to. It's not asking you for the actual y value. So again, as x gets closer and closer to 1, y is getting closer and closer to 3. Part B is asking you to evaluate the function at 1. So that's the actual y coordinate. So the actual y coordinate at x equals 1 is equal to 2. So we can graph functions on our own and use graphs to find the indicated limit, or state that the limit does not exist. So number 3, we're going to graph an exponential function, f of x is 2 to the x minus 2, and use our graph to find the limit as x approaches 3. So recall our time graphing exponential functions. This is an exponential growth that has been shifted down by 2. Remember, exponential functions have horizontal asymptotes, so this one will be y equals negative 2 because of the shift. And then normally exponential functions have a y-intercept of 0, 1, but that's been shifted down 2. It's now going to be at 0, negative 1. 1, 2 would have been on the graph. I shift that down 2. So it'll be 2, 0. And just to plug in 3, 2 cubed minus 2 is 6. So here is our exponential function graph, and we're looking to see what happens as x gets closer and closer to 3. So as we come in to the left of 3 and the right of 3, the graph is getting closer and closer to 6. So the y value, you would say the limit as x approaches 3 of f of x equals 6. So that happens to be the actual y coordinate there as well, which sometimes happens. But again, the limit, it doesn't have to be defined. We could have a hole or something else going on. It doesn't have to be defined at that particular x, although sometimes it is, as it was in this case. Number 4 is a piecewise function, so we need to sketch. F of x is 3x if x is less than 1, and x plus 2 if x is greater than or equal to 1. So remember when we did this before, we point plotted, choosing values around the transition point. So negative 1 is less than 1, that gets plugged into 3x. 0 is less than 1, also gets plugged into 3x. So we have negative 1, negative 3, 0, 0. And then 1 gets plugged into each. So plugged into the top, I'm going to get 3, but that's going to be an open circle on my graph. So the left part of my graph would look like this. And then I would plug 1 into the bottom piece. 1 plus 2 is 3, so that'll fill in the hole. And then plug 2 into x plus 2, that's 4. 3 into x plus 2 is 5. And we're looking at what's happening around x equals 1. So as we come into x equals 1 on the left, and on the right, the y value is approaching the same number. So we would say the limit as x approaches 1 of f of x is equal to 3. And then we have something called a one-sided limit, where we look at either the left or the right alone. And the notation that we use involves a superscript. So if you see x approaches a and there's a superscript of a negative, then that negative indicates that we are looking at the left, and we call it the left-hand limit. So this means as x gets closer to a but remains less than a, the corresponding values of f of x get closer to L. If there's a positive plus as a superscript, it just means that you're looking at the right-hand side. So this means as x gets closer to a but remains greater than a, so on the right of a, the corresponding values of f of x get closer to L. One-sided limits can be used to show that a function has a limit. So if the left-hand limit is L and the right-hand limit is L, then we say the two-sided limit would be L. So if it's coming in to L on the left and right, then the overall limit that we've been talking about, it's called the two-sided limit, would also be L. However, one-sided limits can be used to show that a function does not have a limit. So if the left-hand limit is L, but the right-hand limit is M, where L and M are two different numbers, then we would say the two-sided limit does not exist. So again, if the left and right-hand limits are the same, the two-sided limit will exist and it will be that value. If the one-sided limits are not the same, then the two-sided limit will not exist. So let's look at some graphs where we can explore this. In this example, we're going to look at the limit as x approaches negative 2 on the left-hand side. So here's negative 2. We want values on the left-hand side, so less than negative 2. So as we get closer and closer to negative 2 from the left, the y value is approaching negative 5. Then the limit as x approaches negative 2 on the right, so we're coming at the graph this way from the right. The right-sided limit is negative 1. So as x gets closer and closer to negative 2, y is getting closer to negative 1. Then the overall two-sided limit means put it together. So on the left it's negative 5, the right it's negative 1, and because these values are different, the limit as x approaches negative 2 on the left does not equal the limit as x approaches negative 2 on the right. That means that the two-sided limit does not exist. And we can abbreviate that DNE. So the two-sided limit doesn't exist because the left and right-hand limits were different. And then finally part D, the f of negative 2 is the actual y coordinate at x equals negative 2. So that's the filled in dot, that's where it exists, and f of negative 2 would be negative 5. Alright, let's look at another example. So parts A through D, we're exploring the graph around negative 3. Here's negative 3. So the first part, limit as x approaches negative 3 on the left, so we're coming at negative 3 on the left-hand side. The y value is getting closer to 2. Then we're looking at the limit as x approaches negative 3 on the right, so we're getting closer on the right-hand side. That's also 2. So we're just following these up. The y value is getting closer to 2. The left-hand limit was negative 2. The right-hand limit, was 2. The right-hand limit was also 2. So in other words, these were the same. So that means the two-sided limit is going to exist. That's also 2. And then finally, the f of negative 3 is the actual y-coordinate of negative 3, and that does not exist. There's a hole there. So even though the limit existed, the actual f of negative 3 does not. For parts E through H, we're exploring a graph around 0. So part E, limit as x approaches 0 on the left. It's going to be 0. On the right, it's going to be 3. For the left-hand limit was 0, the right-hand limit is 3. They're not equal. That means the two-sided limit does not exist. And the actual f of 0 is the actual y-coordinate there. Again, there's no filled-in dot, so that would not exist either. And then parts I through L, we're exploring the graph around x equals 2. So the limit as x approaches 2 on the left is 1. The limit as x approaches 2 on the right is 1. The two-sided limit then will be 1 since the one-sided limits were equal. And the actual f of 2 is the y-coordinate at 2, which is the filled-in dot, and that happens when x is 2, y is negative 1.